All right, so what we're going to do right now is we want to figure out the composition of a buffer at a particular pH. And at first glance, first of all, this is so many words, right? At first glance, this seems like a pretty crazy difficult problem. But then what I'm going to show you here is that if you don't know where to go on a problem, you just start by writing things that you know and things that, and essentially by manipulating an equation, you're going to come to your answer. Now, one of the things that's important to understand about a buffer is the best buffers are when the pH of the buffer is equal to the pKa of the acid that's part of the buffer. So you want your pKa of your acid to be very close to the pH. And thinking ahead here, we have Ka right now. And what they've given us is they've given us acetic acid, right? And they're saying, oh, by the way, how much of the sodium acetate should we add to this to create a buffer that's perfect, right? So we're going to work backwards from our go-to equation. The only way we can do that is by using our Henderson-Hasselbalch equation. We know this is the go-to equation. pH is equal to pKa plus the log of the base all over the acid. Now, in this case here, I tend to like writing acetic acid as HAC and the base as AC minus, but since we have NaAC, we can write it like that if we want as well. Now, when we take a look at this, what we're trying to figure out, they've given us the information about our concentration of this guy right here. We know what that is. But we know what they've given us the concentration of this guy right here. They're wanting us to tell how many grams of this we need to add to this to get a pH that's equal to 4.96. So they've given us information there. They've given us information to solve for pH. I mean, not even solve for it, they give it to us. They give us the Ka, which is going to allow us to solve for the pKa. And they give us the concentration of HA. So in reality, if we can figure out what this value here needs to be, we can go from the concentration to the moles and from the moles to the grams of the sodium acetate. So although it may seem a little bit tricky the way it's at, let's rearrange this equation just to get our variables kind of locked in next to each other. So we're just going to go our pH minus pKa is going to be equal to our log. And I'm going to actually use these variables right here, our acetic acid and our acetate in here. If you feel more comfortable writing this in here and this down here, you can go ahead and do that. I would encourage you though, when you write the base down here, it's CH3CO2 minus. This Na plus is not included in our base up here. So I'm going to write it as AC minus on the top and HAC on the bottom. So all things are good, right? We know what our pH is because they tell it to us right here, 4.96. So we're going to put that in right here, 4.96. And we're going to subtract our pKa. Now, how do we get our pKa? Well, they gave us the Ka, and we know that pKa is equal to the negative log of Ka, right? So if we take the negative log of our 1.8 times 10 to the negative 5, we're going to end up with a pKa of 4.7447. So we can subtract that on this side, right? 4.7447. And if I wanted to, I can just do the math of these two. Beep, beep, boop, beep, boop, boop, right? And when I subtract the two, that's so dumb. When I subtract the two of them, I'm going to end up with, on this side, 0.2153 is equal to the log of AC over HAC. Now, here's the thing. We essentially, our goal is we want to figure out what this concentration is. And so here's the pathway. We want to figure out the molarity of the AC. When we do that, we can use the volume and the molarity to figure out the moles. And if we know the moles, then we can use the molar mass to figure out the grams And so our first step is we've got to figure out what this concentration is. Now, the problem is that no one likes using logarithms. And if you're not familiar with what to do here, if you have a log of something, you can take 10 to that thing, 10 to both sides and get rid of it. So if I actually plug if I set this up, I can go like this. I can go 10 to the 0.2153 is equal to AC minus all over hack. And just by well, I don't know what I wrote there. Let me try that one again. Equal to hack. So what we've essentially done is we go 10 to the 0.2153 is going to be equal to these two things. Now, we happen to know a couple things here. One, when we do the math here, this 10 to the 0.2153, boop, 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 is going to give us 1.642. And then on this side right here, we already know they've given us the concentration up here of the acetic acid of 0.2 molar, right? So we can do this. We can plug into this equation, the AC minus on the top we're trying to solve for, and on the bottom we have 0.20 molar. And so we can take this and divide it and multiply it over here. And when we do that, we're going to end up with our concentration for CH. So, I mean, I can show you that we're doing this for 2 multiplied by 0.20, right, is going to equal our AC minus concentration. Again, we've just been doing some manipulation of equations. And then we're going to end up with 0.3284 is the concentration of our CH3CO2 minus, aka AC minus. So we have our concentration right here. And that is kind of a glorious moment right now because remember, if we know our molarity, isn't molarity equal to moles divided by volume? But couldn't we rearrange that and go molarity times volume equals moles? So we know our molarity right now. If we look up at our... Cozy, stop. Cozy, stop. Cozy, stop. So we know what our concentration is. I'm sorry, we know what our volume is right here. I had an angry dog there for a minute. Of 250 milliliters. So couldn't I just go ahead and go, all right, my molarity is 0.3284 molar. My volume is 250 milliliters, which is 0.250 liters. And if I solve for the moles on that, I'm going to end up with my moles being 0.0821 moles. Now, here's what's cool. We need to figure out what the molar mass is of this Na, of the NaC2, I'm sorry, I was going to say C2H3O2, which is the same exact thing. That's been written kind of weird. C2H3O2. It's the same as NaCH, CH3COO, however you want to write it out. But we understand if we have 0.0821 moles of the acetate, we have 0.0821 moles of this whole thing. And they're asking us for how many grams of this whole thing. So if we take this moles of the C2H3O2 minus, we can write that in our equation, go 0.0821 moles of NaC2H3O2, which, by the way, that is this right here, the formula. And if we look up the molar mass for NaC2H3O2, it's going to be 82.03. Oops. Should probably set it up so that it cancels correctly. We know that for every 1 mole of NaAC, we have, and this is from the periodic table and adding them up off screen, 82.0313. And when we do the math on that, we're going to end up with 6.735 grams. We need 6.735 grams. Now, they've asked us to solve it to 2 significant figures, and so we're going to end this with a 6.7 grams. This has been a little bit hectic, and if you walk your way through this here, you might want to rewatch the video. And then when you try other problems, realize it's going to be just manipulating the equations. Hopefully this has been helpful.